Hello, everyone. This is Professor Ma, and this is the section on L'Hopital's rule, first part. Okay. We have previously, for limits, if we have elementary functions, simple ones, if one is limit x equal to 0 of 2 cosine x divided by 3x plus 5. If you can plug it in this case, if I plug in cosine 0 is 1, so I get 2 on top, and on the bottom I get 5. Then the limit would be 2/5. So if I can plug in, I get a concrete numbers for elementary functions, and that will be the limit. Where do the problems comes in? Well, it depends on the form of the questions. In particular, there are two forms that in the fractional form, the group in green, shaded in green, and then there's these exponential forms that causes problem. Recognizing, it's difficult, somewhat more difficult to tell how to find the limits. In particular, let's take a look at this fractional form. Okay. And the infinity times 0 is in multiplication, but I can always write multiplication as a division. So therefore, that's actually a fractional form of the top. Okay. And I listed a bunch of examples just by saying, basically telling that by looking at these examples, that the plugging in the numbers fail to tell us anything. Okay, because what the examples, there are various examples, plugging in all these examples, the effect is the same. I wonder we're looking at the same thing. But in reality, the limits of each example go to different things. For examples, x over x, as x goes to 0, or x over x is 1, so this goes to 1. X squared over x, this is 0 over 0 if I plug it in, right? But you say, well, of course, I should cancel the x, but that's actually equal to x. So this one actually go to 0, x goes to 0, because it basically just x. Then on the other one, this one goes to infinity, because this is basically 1 divided by x. Okay, again, what's the moral of this story? The moral of this story is when I plug it in, I get the same, I'm staring down the same 0 over 0. And at this point, I have to decide what the limit of the formula is. And because there are 3 possibilities, therefore, at this juncture, I have to do something else. At these junctures, I have no answers. Okay? Therefore, we call this ambiguous form. Means I got to do something. Okay? Same thing with the other cases. And I list a bunch of for the infinity over infinity. Okay, and it's a kind of mirror image of 0, 0. In fact, any problem phrased in terms of x go to 0, it can phrase in terms of some x go to infinity, okay, by putting u to be 1 over x and change every seconds. Okay. And then the second batch, as I was talking about, is something raised to a power. Okay. We'll see these, okay, when we see that, okay, in particular, when we see 1 over x power, as x goes to infinity, so this goes to 0, so the things we think about is like 1/2, 1/3 power, 1/4. So actually, these are asking to take roots. Okay, so in particular, this problem is asking you, say, hey, what's the square root of 2, cube root of 3, 4th root of 4, 5th root of 5, and this is a little bit hard to recognize. You can take a calculator, punch in, and kind of guess, this thing seems to be going to, the answer is 1. We'll see that, okay? So in relation to similar to this type of problem, we have this exponential limit problem. Okay, that's that so-called ambiguous forms. Okay, so in this example over here, when x goes to infinity, this goes to 1. But in this case, when x goes to infinity, the base goes to infinity, the power 1 over x goes to 0. But notice 1 over x times x is cancels out. And so this actually is just x. And as s goes to infinity, x of course goes to infinity itself. So in other words, just because I recognize this x infinity that goes to the base become infinity, the power becomes 0, taking roots, I really couldn't tell which case it is. Okay, what's happening to the limit. So this is another type of ambiguous problem. So this basic 2 types. In this section, we're going to do the top one. Okay, and the next section we'll do the bottom ones. And here is the another PowerPoint explain what we mean by ambiguous form. So when you plug it in, you get 0 divided by 0 and 1 divide. And in this case, okay, we get some things depends on who goes to 0, faster or slower. Okay, so I couldn't tell the limits. So that's why we say 0 over 0 is ambiguous form. So when you plug it in, you get 0 over 0. What do? We stop. We have to go back to the problem, reprocess, and do something else. Okay, so where do we get ambiguous form from? Again, we get ambiguous form from divisions, okay, numerator and denominators, and taking exponents, okay. And when do we get into ambiguous situations? Well, when both the top and bottom of the fraction go to 0, okay, or when the top and bottom both go to infinity, they get bigger and bigger, both parts. Okay, and similarly, so in other words, we will have troubles. You might have trouble when in the fractional form. So in exponential form, you get 0 or infinity. So if I stick 0 or infinity into fraction or exponential form, I get all these different possibilities. Okay, 0 over 0 in the fraction, infinity of 0, 0. The one shaded in green, we know what the answer immediately is. This big number divided by small number, this is big. Okay, if I slap absolute, so I know the behavior is going to be a large in absolute value. And this goes to 0. Okay, if I take a power, very large infinity power gets bigger and bigger. The base is very large, gets larger and larger. Of course, this blows out to infinity. And similarly, if a number gets smaller and smaller, and I raise it to a higher power, like 1/2 square, 1/3 cube, 1/4 fourth, these things of course go to 0. So these 4 forms are not ambiguous. Okay. So remaining 4 forms are ambiguous. Okay, and so. Here is the some more examples of the ambiguous exponential form, which actually we're going to deal with in next sections. And I'm going to leave you to read these and think about it. And we'll come back to these in next sections. Okay, so we're going to deal with the fractional ambiguous one. Then what's the basic rules that we're going to use that to help us to find the limits? This is called the L'Hopital's rules. Okay, and it's simply stated is if you get a fractional form, some formulas, and when you plug in the number a, if you want to find a limit as x approaches some number a, and if you plug it in, you get a 0 over the 0 form, then you have a surrogate formula that you can use. And the surrogate formula is take the derivative of the top, divide by the derivative of the bottom. And that is, the limit is going to be the rate of f at that point. 0, or the output is 0, but the slope, and that is going to be the ratio of the slope. So it's kind of obvious in that sense. Okay, even though it's a 0 over 0 form. Okay, so like this, for instance, the L'Hopital's rule say if I plug in 0 for, first check it is ambiguous. Plugging 0, I get 0 over 0. So we had a proof for geometries of why this is true. Okay, I'm not, but here is using the L'Hopital's rules because I put it in, I get 0 over 0. Okay, so I apply derivative to the top and find the slope for the top at 0, slope for the bottom at 0. Slope for the top sine x is cosine x 1, 0. Okay, so 1. Sorry. Okay, so the limit of this is 1. Okay. Okay, so therefore, if I apply the L'Hopital's rules on this important formula, I get in one step. Okay, and I want to remind you the geometry proof. The geometry proof is that x is the angle, will be the length from here to here, and here's sine of x, and basically this is it traps between these two lines. You squeeze it. Okay, that's how the geometry proof. And here is derivative proof, L'Hopital's proof. Okay. Again, this one plugging in, you get 0 over the 0. So take the derivative of the top, take the derivative of the bottom, see the rate of at x approaching 0. Then you get the derivative of the top, it's x approaching 0. You get 1, then you get the answer 1. Okay. But if I put x squared on the bottom, okay, then I will get an extra x now on the bottoms. And as x go at 0, and that makes the denominator become 0, okay, from the positive side. Okay, so I'm not going to worry about jumping around positive, negative. So on the positive side, therefore the limit goes to positive infinity. Okay, because the top goes to e to the, as x goes to 0 plus, the top goes to 1, it gets closer and closer to 1, the bottom gets closer and closer to 0. Okay. How about something like that? The way we do these, okay, first of all, the problems over here is the x in the denominators, and so basically we split this into two parts. I'm going to put this into a fractional form. Okay. In other words, just put the 1 over x on top, plug it in infinity, and I get top goes to 0, and this becomes 0, and the sign of 0 is 0. So the whole thing in the denominator goes to 0 also. So this is a 0 over 0 form. So I can apply L'Hopital rule, take the derivatives, top and bottom, find the slope of top and bottom at x approach goes bigger and bigger. And this is the chain rule, okay? Cosine of 1 over x squared, right? And times the derivative of this is u prime. And here's the trick, and that this minus 1/3 will flip up and cancel with x powers on top, okay? And leave you 1 copy of x. Now you can plug in infinity, okay? And that's going to be infinity. Why? Because cosine of 0, but this part goes to 0. The cosine of 0 is 1, 2 times 1 is 2. x keep getting bigger, so this goes to infinity. Remember, you got to check the conditions, okay? Here, you cannot just say, oh, x go to 0, so let me use L'Hopital rule. No, no, no. You have to check that the top and bottom, they both go to 0. Here, the top goes to 0, the bottom goes to 3, 2. These go to 0. So this is 0, but 2 is 0. And you cannot say, oh, use L'Hopital rule because you get wrong answers. Same thing for going to infinity. L'Hopital rules apply if the numerator and denominator go to infinity. And so this we use L'Hopital rules for the infinity over infinity ambiguous form also. So for example, if I plug in infinities square, it gets bigger and bigger, and the bottom gets bigger and bigger. It's also square. So the L'Hopital's rule says, I can use the surrogate, the derivatives. Okay, so I take the derivative top and bottom. I get a linear functions, and if I plug it in again, it's in the infinity over infinity. So I may apply the L'Hopital rules again. I have to. And now I get a concrete answer, 3/2. Okay. And this is the same trick as we did before, divide everything by the highest power x squared, divide by x squared, x squared, x squared. And then all this one cancels out. And what you're left is 3 divided by 2. Remember, head divided by the head. This is what L'Hopital justifies. One of the important things about using L'Hopital rules in general is it classifies the formulas, the exponential formulas, the power formulas versus finally the log formulas. And you have these orders. Okay, when x goes to infinity and the p of x down below, I'm using a polynomial, any polynomial. Okay, then let's say here's e to the x. Okay, and here's x squared. Okay, x squared in the beginning, here's x squared. In other words, e to the x in relationship to the formula x squared, e to the x takes out a lot faster. So the ratios that blows up to infinity. Okay. In particular, the proof is this because I use L'Hopital rules and the derivative of e to the x never change. So derivative of e to the x is e to the x. But the derivative of a power function, say a polynomial, the degree of the polynomial become 1 less. So if, for instance, x is to the 5th, after I take a derivative, it will be 5x to the 4th. So the new question is, well, what's the limit of e divided by 5x to the 4th as x goes to infinity? This is the derivative, the L'Hopital rule says. Well, I do it again. Then if I do it again, then that's going to become 20x to the 3rd power. So we realize if you keep doing this, the top doesn't change. So eventually I wind up with the bottom to be a number. So the top x goes to infinity, then that goes to infinity. Okay. So the moral of this story is exponential formula goes to infinity a lot faster than any polynomial. And likewise, any polynomial to any power, actually even square root of x, for instance, x is 1/2. P is 1/2, then I'm talking about square root of x. If I'm asking square root of x over log x, okay, when x goes to infinity, where does this go? Well, it's infinity over infinity form. So I can take the L'Hopital rule, apply to it, and apply to it once, and okay, and then we have it. Okay, and let you read about these, and basically you got x to the p power left, and then because p is positive, then goes to infinity. Okay, so any power function goes to infinity a lot faster than log function. Okay, so for instance, this is the square root functions. Okay, y equals square of x is a power functions. Okay, and here's log functions. Remember, log goes minus infinity. Okay, it goes up very, very slow. Okay, at 1, 0. Okay, so power divided by log, the ratio is infinity. Okay. This is a problem where we change a problem into a infinity over infinity form and apply L'Hopital. We get a little trigonometry, then we wind up with answers. Okay, so this is the problems for L'Hopital's rules. Okay, that's it. Bye-bye.